So
And yeah, I don't know how much you overheard, but Tara is basically a grad student from the lab. The previous grad students that gave a talk were the first in the lab, and then Tara basically was the second generation, as is Jeremy Neumann. I think he's the second and a half generation who is talking next week. So I would say, Tara, take it away. And again, if you guys cannot see it from the side, feel free to move to the middle.
thank you. All right, I'm excited to be joining you all virtually today. I was WIM's grad student that now has moved on to a postdoc in Colorado, and I'll tell you a little bit about what I've done. I took sort of a big turn when I switched to my postdoc. But today, what I really want to talk about is how I can take these two very different types of neuroscience and combine them and use a lot of the skills that you're learning in your class right now. So if you guys have any questions, please feel free at any point to just stop me, ask. This will be very casual. So just to kind of go over where I'm coming from and the background that I've started with. So when I was at University of Chicago, my focus was really analyzing these intracranial neural recordings in humans and thinking about the spatiotemporal seizure dynamics. So a lot of similar to what you guys are probably talking about in class. A lot of these actual electrophysiological recordings, thinking about how we consider them as signals, how do we process those signals, and what can that tell us? Then when I switched to University of Colorado, I actually went very strongly in the other direction towards mathematical models. So I sit in an applied math department now. And my work was focused on decision-making models. So how is it that we interact with the environment to make a choice? And what does that look like in terms of our actual strategies? So way more on the behavioral side, thinking about cognition in the context of decisions. So moving forward, what I've been doing now that I'm starting to reach independence is the idea of how do we combine these two? So I'm still at the University of Colorado, but what I'm now spending a lot of my time thinking about is how do we think about cognition and the neural mechanisms that can support them? And specifically, what I'm curious about is what we're going to call a latent environmental feature. So this is something that's happening in your environment that educates our cognitive strategies. But the question that we don't really understand is how do you access that? How do you know about those features? And how does your brain then use that information to modulate our behavior? So today, the way that we're going to talk about the methods that go along with comparing cognition and neural mechanisms is that we have to focus on one particular area of cognition to get ourselves started. So today we're going to talk about decision making. And so just because I don't know how many of you are familiar with decision making in general, let's just start with what are the elements of a decision. So generally, when we think about making decisions, we can break it down into three main pieces. So on the one hand, we're going to have the piece that we call the prior. So this is the belief we have coming into a decision. So it's what do we think the best choice is before we even have any evidence. Then the second piece along with that, which is probably pretty obvious, what is the evidence we have? So there's information in our environments around us that's going to educate our decision. So we're going to incorporate that into that belief. So then the third element that we have to consider is how do we combine our prior and our evidence? So we can call this a decision rule. If we talk about this a little bit later in terms of Bayesian work, we would think about this in terms of likelihoods. But really, all these elements exist, but we don't have access to all of them directly. What do we have access to is just a choice. So this kind of complicates things because if the question that we want to ask is, how does your brain store a prior? Or how do we incorporate these pieces of evidence? We need to think cleverly about how we can actually access those questions when all we know is the choice, yes or no, in a lot of ways. So In order to do this, let's just lay out the strategy and the methods that we're going to go through today. So we can have our decision elements, and we're going to just say that the way we're going to approach these questions then is that we need to identify a task. So what kind of a cognitive task can we use in order to get at the question we want? Then we're going to actually build computational models. So we're going to start with a modeling component and say, okay, what are the strategies we think could underlie this? Then we're going to compare this with data. And since this is a methodology class, we can think about this in two ways. So I'm going to focus on two types of comparisons with data. On the one hand, we're going to think about how do we do behavioral comparisons? So how do we look at just those choices and use that to interpret our models and human responses? And then we can also talk a little bit about drawing from signal processing methods and how we can do that in a few different ways. And then sometimes, although not for all of the projects that we'll talk about today, what we would do after we do these comparisons is that maybe we want to go back and we can actually update our models in order to improve on them. So that's the goal of what we're going to be doing. And so for the rest of the class today, what I want to do is just show you examples of how we can really do these steps with a heavy emphasis on this comparison with the data. But before I jump ahead, are there any questions on just decision making or anything? We good? Awesome. I can't actually see anyone, so if there are questions, you'll just have to speak up.
They will, Tara.
Okay, perfect. Okay, so let's start now with the question. Oh, yeah, we're going to start with behavioral methods, focusing on specifically one form of comparison with data. So let's start with this question. How can we encode and update our environmental beliefs? So our environmental beliefs could, again, be those latent features. They could be something like, what is the frequency I think the weather will change, right? Maybe something like that where, do I need to carry an umbrella? Do I think it's rainy season? Should I bring a coat? That sort of a thing. So in order to do this, we can start by just sort of breaking down what are the components we would need to ask this question. Well, if we want to encode our environmental beliefs, what we really need is a system where we can store this information and then later access it to retrieve it. So in the brain, we're going to say that this is comparable to working memory. So we're going to focus on our working memory as our system. But now there's another piece that we're going to need. We don't just need to store and retrieve. Environments change around us. So we also need to be able to update this system. So this could correspond in the brain to the idea of needing flexibility. So we're going to say that mechanistically, that's the same as synaptic plasticity. We can think about which rules might help us do that. But there's one other thing that we need to consider in order to answer this question, which is that we don't have unlimited resources. We also need to think about our data compression and resource allocation. What is it that's important to us, and how can we store that in a meaningful way? So if we want to put this in terms of neural mechanisms again, we can think about this as efficiency. So how can we efficiently encode these environmental beliefs? So we now have a question. It's a cognitive question, but based in neural mechanisms. So we're going to go through step one, and we're going to say, okay, what's a task we can use to ask this question? Well, what we can do is start with visual working memory. So one very, very common visual working memory task is something like this, where what we're doing is we have a fixation point, and now we're shown a cue. And in this case, the cue is a location and a color. So we have this little purple box. And now the cue is going to disappear. We have a short delay, so on the order of seconds. And now you're asked to respond. So you're prompted again for that location. And you're asked, what color do you remember? And you're given this little cursor, you move it around, you give your response. And this task was given to a lot of human subjects online, and something pretty interesting came out, which is that when you look at the reported colors, here, this black trace is the actual distribution of colors that subjects were shown. But if we look at the density of their responses, we see that certain colors were overreported in comparison to that more uniform target distribution. So at first glance, we can see this and we can say, oh, well, maybe humans, we just have limitations, right? Maybe we only remember certain colors better than others. We have these biases. It's just a flaw. That's what we can perceive. But another way we could think about this is the idea that rather than it being a limitation that's a deficit, that this bias might be because we have a heterogeneous environment. So what if instead we said that certain colors of our environment are more represented than others? Well, now we have an interesting conundrum. So is this a flaw or is this something that's beneficial? In order to answer this, we're going to build some models and ask the question whether incorporating a belief that the environment is heterogeneous, so a belief that these colors are going to be represented in different ratios, is actually useful. So in order to do this, we need to take kind of a back primer step before we jump into that model, just to talk a little bit about what working memory is and how we're going to model it. So when we talk about working memory in this project, the way that we're going to describe it is the idea that we have our excitatory neurons, and they're going to have a preference for a particular form of the feature. So here what I've done is I have modeled all of these circles are going to be excitatory neurons. They all have a preferred color. And they're going to be connected in such a way that excitatory neurons with similar preferences are more strongly connected. Now, on the other side, we have inhibition, and we're going to have this broad spanning inhibition. And what this does, if we were to model this and look at what the activity of this network looks like, is that we get a bump. So we get a bump of activity where those excitatory neurons are going to activate, but inhibition is going to dampen it so that we have just this small amount of network activity that represents the color that we saw or are trying to remember. So if we look in time, we see that this does have some amount of noise, but the convenient thing is by looking at where this bump of activity is, we can read out at the end of some time period what our response would be based off of which of those excitatory neurons are actually active. So if we put this back into the question about, well, how does this relate to our environment? It allows us to break this down into two pieces. On the one hand, we can say that long-term environmental beliefs can be encoded in synaptic connectivity. So how these are connected to one another and the weights of those particular connections can actually influence and describe our environmental beliefs. And we'll go into what that means in just a minute. Whereas our short-term choice, that cognitive behavioral response, right, the thing we can actually read out, that's going to be encoded and represented by our neuronal activity. So the location of that firing bump. So this is how we generally think about the idea of working memory, especially in this type of a task. But there's one problem when it comes to interpretability. Remember, what we want to be able to do is think about the neural mechanisms, but in the context of a behavioral response. So these bumps are great, but we can simplify this even further, which will make the rest of the analyses easier. We can think of this bump instead as just a particle, and that particle is going to move in some way through a landscape. So we're going to make a simplified model of this. So particle model, when we talk about this, we can think about this in terms of here is our bump. Now it's just going to be this particle, and landscape is going to describe synaptic connectivity. So if everything is connected with the same weights across the network, we can say that it's homogeneous, in which case there's only going to be diffusion that acts on this bump of activity, or now particle, right? So if we see what that looks like and we look at the trajectories, let's say that we have a bunch of different locations that we start at. Each of these traces then, in time, this is just diffusion, just noise of our particle moving. The problem is now, how do we incorporate those biases that we saw? If we think that this is an environmental belief, and we say that environmental beliefs can be modulated in synaptic connectivity, let's change that landscape. So now what we can do instead is think about a landscape that's heterogeneous. So we're going to have peaks and valleys or troughs. So just like it's easier for you and I to go down a hill than it is to go up, our particle is now also going to be drawn into these wells. So there's particular locations that they're going to prefer. So now if we look at what the trajectories would look like for a particle in this kind of a model, what we see is that our particles are going to still have that noise component, but they're drawn to these troughs. So now we have two forms of this. We can ask, okay, if we do have these heterogeneous environments, is there a benefit to those biases? Now we have a way to actually compare this. And the way that we're going to compare this is to use a behavioral metric. So what is our behavioral metric? Well, we're just going to use what we call distortion. So pretty much just error. How far is your response to the actual original color? So here we just had our target, we have our response. What's that error difference? And what we can do is then look at this for different colors within our actual environmental distribution. So let's say that we're in this nice landscape, it's homogeneous. Well, if we look at the responses that we'd expect from this kind of a model, for a common color and a rare color, we get the exact same distribution of responses. So we're going to have the same average error because there are no biases. There's no reason that we would expect there to be a representation. Now, on the other hand, if we have our biases here, right, we have this heterogeneous environment, what we see is that for common colors, now our model shows us that the responses are much narrower. So it means that our distortion, that error is much less. We're actually doing much better for those common colors, but it comes at a cost. For rare colors, we're being drawn to these other points, these wells up here. So we actually have much bigger distortion. So now the question is that benefit of having a narrower distortion for the common colors worth it? So what we can do is we can just say, okay, what is our overall distortion? So how wrong are we across all the colors? And compare that to this baseline. And when we do that, we can vary how many wells. So how much of this landscape, how many hills and valleys do we have? And what we see is that we always get this, after just a few wells, a reduction in error for heterogeneity. Now, what's really important is that we get this reduction in error even if we have more wells than there actually are peaks in our environment. So it doesn't have to match exactly, but just having biases is actually really beneficial to us. So this is our first key piece of evidence. We have this model, we have a behavioral metric, but now we have a couple more questions we need to, and bells and whistles we want to add to this model before we can dive into whether or not humans do this and how this relates. So the big question is, we started with this, we said, great, we have this heterogeneity. These biases are actually really useful. We can see that we have these different numbers of wells. How do we learn that environment? How do we know which colors are common and where those wells should go? So what we're going to do is we're going to take this particle model and we're going to expand it one more step and make what we call an experience-dependent particle model. So now let's envision that we've never seen a color before in our life. What we can do is we're going to draw from the idea of probabilities. So now we're fresh to the world. All of a sudden, we see a color. This is our first color that we've ever seen, what we're going to do is we're going to update our prior, so that belief about the world, and say, well, I've seen green. If I've seen green now, the chances are I can see green again in the future. So that's an important thing for me to know. So what does this mean? We can update our particle model by changing the landscape. And we're going to put a well right where that color would be. So now we see a second color. Again, we can update our prior and we can update our landscapes. So if we continue to do this, what we can do is actually build back after many, many experiences a prior that matches our environmental distribution and corresponds with wells at those most common colors. So this makes pretty logical sense, right? We're essentially just updating our model based off of what we see. But the goal of this is to say whether or not this is what humans are doing and whether or not this is useful. So this brings us to, how do we do these comparisons to actual data? We have something that we're using as an approximation of what the brain is doing, but the only thing we know about actual humans is their behavior. So in order to do this, what we're going to do is ask the question, which type of our models can best match a human response? So now if we go back to the task, remember we had this color we saw, we have some sort of a delay, we're asked to report the color. In that original task, there was a pretty uniform distribution of colors that we're using. But now we actually have data from a second set of this exact same type of task, where instead certain colors were overrepresented. So they were asked about certain colors more. Now, what's really important is that not only was there a heterogeneous environment, but it was offset. So this means that every subject got random distribution of where these peaks would be. So maybe for some people it was purple, for some people it was shifted a little bit to the right or to the left. So this means that they're not necessarily going to have peaks that are aligned with their natural baseline biases. So, well, what kind of models are we even comparing this to? We're going to ask about 3 kinds. On the one hand, we can ask about static models. So in an environment that's homogeneous, one that's heterogeneous but fixed. There's no learning in it. And the third type is that experience-dependent learning, where we're going to update with every experience they are given. And then there are a few subversions of this, but we're just going to stick to the 3 basics for today. So how do we actually go about comparing these two? Well, we can go back and remember that we said the location of the particle at the end of the trial is the same as a response, because we said that was the same as looking at where that bump of neural activity is. So what we can do is then use cross-validation. So what we're going to do is that we're going to take the responses from a human subject and put those to the side. And along with those responses, what we have are the data. We know exactly what colors they were prompted for. So cross-validation means that we can train our model on 80% of the trials. So we're going to ask for each of these 3 types of models, we're going to try to fit the best parameters. So this could be things like how many wells there are, what is the amplitude we're expecting, how much noise do we expect in our model. And we're going to train that for 80%, and then we're going to test it on 20% of the data and ask, okay, here's 20%, give me my model-based responses. So we simulate those 20% of the responses and we consider the error. How similar were those responses for our testing set to human responses that were given? And whichever ones had the lowest mean squared error on the tested data are the best match. Now, we're going to do this 5 times. Why are we going to do it 5 times? Well, we're always testing on 20%, but we want to be sure that we test all of our responses. So we're going to do this so that we split it up and do 20% each time. So this overlap allows us to make a bunch of simulations, get the best set of parameters and model fits for each of our models, and then actually ask the question, which of those 3 models best matches the responses? So when we did this, what we found is that subjects actually show the most match to the learning models. And this was regardless of if they had very short delays or very long delays. So what this did was say very reassuringly that, hey, we are updating our beliefs about the environment as we're exposed to these new features and as we have each of these new trials. So our subjects were learning these new underlying distributions. So we had this data, we used our behavioral method to come up with proof that this makes sense. Now, the problem is we need to go back one more step. So in this case, we're going to actually go back and update our models because particle models are pretty simple. At the end of the day, a landscape and a particle is a great representation, but it's not great at telling us what exactly the brain can be doing. So what we can do now is take what we've learned and build a more mechanistically realistic model. And so what we're going to do now is say it's going to be a neural field model. So let's go back to the idea of having neural activity and synaptic connectivity. So now that we've seen that we can vary those connectivities to get biases, we can build that same type of static model to start. So in one case, we can have our excitatory weights be completely uniform. So that's just like our homogeneous model. In the other case, we can have our connectivity actually modulated. So we have stronger peaks versus these weaker points as our heterogeneous model. And just for proof of concept, we can take a look here, and what we see is, great, in our homogeneous model, if we start our neural activity, we see again, just this diffusion. If we look at our heterogeneous model, we see that we have these biases. So this common color is going to be retained better, and a rare color is going to be shifted over to wherever that strength in connectivity is. Now, if we want to take this one step further and get to the idea of an experience-dependent mechanism, what do you think we need? How are we going to change the connectivity? What tools do we have in neuroscience to change connectivity between neurons? No guesses? Okay, so what about plasticity, right? We have plasticity mechanisms that we can use. So in this case, what we can think about, because we're looking at environments on longer timescales, we can think about changing our excitatory connectivity using long-term potentiation. So these neurons are going to activate, and we're going to say, great, I saw this color. These neurons that were excitatory neurons with similar preferences were activated. We're going to increase that strength, right, of connectivity. And so we're going to incorporate these with each experience. We can build upon this such that over many, many trials, just like with our particle model, we can actually modulate our connectivity strength. So we have these peaks where we have strong connectivity for common colors and this weaker connectivity for weaker colors. And if we actually look at what happens to our overall error when we do this, we can see that rapidly, as we're learning our environment and changing that connectivity strength, our distortion goes down. So our error is improving, we're getting less error. And we were able to come up with a mechanism for that based off of only what we saw in people's behavioral responses. All right, so what this really tells us then in conclusion for this project is that we can look at something like environmental beliefs and represent that in synaptic connectivity. and that rather than being a limitation, these biases can actually be part of an efficient coding mechanism. It's allowing us to be really accurate for colors or features of our environment that are common and that we want to remember well, while bypassing putting in extra effort for things that aren't going to come up very often, for those rarer colors in this case. All right, so before we jump into a different project, are there any questions or comments about looking at sort of neural models, but with behavioral data? All right, well,
They have a hard time to decide what to ask.
okay. Well, if you come up with any, we can talk about things at the end. Maybe you'll be inspired through the other projects too.
Okay.
So just going from here on, we talked a little bit now about how we could use a behavioral method to understand a neural model. But now, what about more signal processing methods? How can we use some of the things that we typically think about only in the context of electrophysiology, but in ways that actually complement and allow us to get at some of these more cognitive questions? So the version that I want to talk to you about today, we're going to talk about specifically triggered averages. So there's 3 categories of a triggered average that I want to highlight today. And I've used them all differently in very different contexts. So just to start off, when we talk about a triggered average, what we're talking about is selecting a feature. So it can be something like the spikes that we're seeing. It can be something like a particular part of a task. It can be something like a particular feature of a behavior, and aligning whatever that signal is that we want to those particular points in time and windowing it out and averaging. What this lets us do is then ask the question, is there something interesting and meaningful happening at the surrounding times that maybe tell us something about those relationships? So just to start off, the one that I think most people are familiar with, at least in neuroscience, is the idea of a spike triggered average. So this is something that women I used in my graduate work. And the idea is that here we're really comparing neural data to neural data. So in this project, what we were doing is that we were interested in the relationship between spiking activity during a seizure and low frequency activity. So looking at the LFP. So in this case, what we were doing was actually looking at recordings from what's called a Utah array. So what this is a microelectrode array. So it's a 10 by 10 array of electrodes that allow us to actually record from units, so single and multi-unit activity, as well as getting some of those lower frequencies. So if we break down what this looks like, then we could say that one of these electrodes is going to give us a train of spikes that we can extract. And if we align that spike train and look at what's happening in the LFP and do that windowing technique, so we're going to pull out each one, we're going to average them. What we're able to do is to actually look at, here we labeled it STA. What does that activity actually look like? So here we were looking specifically at what happens in the center of a seizure, so what we would call the ictal core. And there's a couple of ways that we can interpret this. So in addition to looking at the signal itself, which is the black trace, we can think about what happens when we randomize when in time those spikes happen. So that would be equivalent to bootstrapping, right? We want to know how meaningful that signal is. Is it really related to when these spikes are happening? And the way to ask that question is, well, what if I pick random times? So that's going to give us one form to understand this. And the second one in this case is what we did was noise. So what we did was remove the main features of the signal And so in this case, epilepsy has oscillations during seizures, so removing that oscillation component, and again aligning it and seeing that there really wasn't anything left. So these were confirmations. These are ways that we can go about and understand how strong this relationship is. So this is when we want to compare neural data and neural data. That's one way to do it. But what if now we want to get back to that question of how do we interpret behavior and use these same signal analyses techniques? Well, we can think about this in two forms. So what I want to do the second half here is think about evoked behavior. So how do we use the same idea, but now instead of neural data to neural data, we're going to think about aligning a task feature to behavior and treating that behavior as our signal. And we can think about evoked potentials. What happens when we actually use the task or a particular behavioral feature and compare it back to neural data again? So what we're going to do is now break these down, and I'll tell you about the evoked behavior, and then I'll tell you a little bit about the evoked potentials, which is a pretty new project. So I'm excited to share that with you. So starting with this evoked behavior. So what was the first step we needed? Well, we need to ask a question. We need this task, right? How are we going to use this? Well, the question we're going to ask is still about the environment. And specifically, we're going to talk about something that I'm going to call hierarchical inference. So that last part that we were presenting on, we talked about the idea that there's these environmental beliefs that we're updating and we're keeping contained so that we can actually use it to modulate our behavior. But how do we actually learn this? We asked about how we could update our beliefs, but how do we know to update our beliefs? Well, we have to infer particular features of our environment. So the task that now we're going to consider is what we're going to call a binary hazard task or a hazard switching task. So a really basic form of this, if we think about decision making, is going to be a two alternative task. So maybe the task is something really simple. You're going to see dots moving on a screen, and they can move to the left or they can move to the right. And we're going to call that state S minus, and that's state S plus. So typically, people do this task all the time. They just ask the question, which direction were the dots moving? But now what if we add in a latent environmental feature? So not only do the dots move to the left or to the right, but they actually switch between those two states with some underlying hazard rate. So what's a hazard rate? Well, it's going to tell us the probability of switching. So if I have a high hazard rate, I switch between two states pretty often. If I have a low hazard rate, I rarely switch. So you can think about this as the underlying dynamics, right? That's part of our environment. If we go back to the idea of the weather, maybe if you live in the desert, it's probably a very low hazard rate that you're going to switch to rain, right? But if we live in a place like Colorado or Chicago, where the weather is much more variable, it's a high hazard rate. So why do we call this binary hazard? Well, in this case, we're just going to say there's a high or a low. Let's make it easy. We're not going to have lots of options. There's just two. So let's start with thinking about what does a hazard rate look like? Well, if we have a high hazard rate, then we can see in this case, we're going to have our dots move to the right. There's some sort of a change point. We don't know the change point happens, but what we do see is that the direction changes, right? So in this case, we can get to the end of the task and we can say, okay, I'm going to ask what my current state is. And so we can see the difference between a high hazard rate and a low hazard rate is how many change points occurred. So why do we even care, right? If all I'm asking is, what is your current state, right? At the end of this trial, are you in the left dots or the right dots? Why does knowing the hazard rate matter? Well, if we think about how much information we need to use for our decision, we can see there's a big difference. So if it's a high hazard rate, the amount of relevant evidence in our task is only going to be that little bit right at the end after that last change point. Versus a low hazard rate, we have a long time that actually is relevant. So by knowing what that hazard rate is, we know how much information we should be using and how much information in the past can be discounted. So here's the problem. We don't always know what that underlying latent feature is. We don't know that hazard rate. So how can we learn it? We need to figure out those change points. So if we look and actually either count or identify when those changes occur, we can update our belief about the hazard rate itself. So we have this task. The task really is going to ask the question, how do we learn this hazard rate? And how do we do this? Well, we need a model that can do the same sort of behavior again. Now, in this case, we're not going to use a neural model. We're going to use an actual behavioral strategy model. So we're going to think about this in terms of Bayesian inference. So for those that may have had probability in the past, all we're going to say is that we're going to use a decision rule. So remember, we had our three components, our prior, our evidence, and our decision rule. We're going to look at our log likelihood ratios. So this is just going to ask the question. Oh, sorry, was there a question? No. Okay. We have one equation that's going to help us track our state. So what's the current direction, right? So that we can answer the question, the current state at the end. And one that's going to update our belief about the hazard rate. And so in the state log likelihood ratio, we can just determine this information explicitly. We just look at which direction those dots are moving. And we can write this in terms of probabilities as the probability for a particular time that I'm in that S plus, so that right moving dots, for a given hazard rate over the probability that I'm in S minus. And so we're just going to say that this H is whatever we believe it to be. So how do we know what hazard rate to use? Well, we're going to do the same thing and keep a ratio going of the log likelihoods for the hazard rates. So now this is that latent feature. We need to identify those change points. And now we're going to ask, okay, well, what's the probability that I'm in either state, but I'm using a high hazard, and the probability that I'm in either state, but I'm using the low hazard? So really, this means we've got 4 options, 4 different possible environments we're in at any given point. So what does all of this have to do with those average triggers, or those triggered averages that we were talking about? Well, what we need to do is think a little bit about what does this model look like? So now, instead of looking at neural activity in time, we'll look at behavioral activity in time. So what we see here is on our time axis, if we just look at what Y hazard and Y state would look like, and here what I've done is I've marked what the current states are, so either S plus or S minus, and these dashed lines show us where the changes actually occur. And we can see that our system, like if we just look at where this green example is, updates. So here, our belief was in favor of S minus down here. The change occurs and we say, oh, okay, our belief is changing, updating. Now we're believing that we're in S plus in this new updated state. At the same time, once we switch here and we recognize that there's a change point, we see that we get a bump in our belief about the hazard rate. So now we think, oh yeah, it is probably that higher hazard. But the longer that we spend in that same state, slowly we decay again. Because maybe we start to think, I haven't seen any changes recently. Maybe it actually is that lower state. So these 2 pieces are balancing each other. Our belief about our state and our belief about hazard are coupled. And they're letting us do that hierarchical inference and answering the question of how we're updating. But what we need to do now is we really want to know what's happening in the behavior right at these change points. What does that update look like? And how can we use that to understand what people are doing? So in this case, we can go back to that idea of evoked behavior. And what we're going to do is we're going to align our behavioral model to those change points. So here, this dashed line is going to be that change point. And if we average what the accuracy looks like, so how long does it take us to realize that our state changes after a change point, we see that depending on whether or not we're in this lower hazard, which recovers really slowly, or a higher hazard, which recovers really quickly, we can actually see those differences just by averaging. So this is in our model. And what does this tell us? Well, there's a few important things we get out of this. On the one hand, we can pull out from our averages what we can call a recovery slope. So how quickly do we actually notice an update and use that information? The other one is how accurate can we get? So we can call this our steady state, the probability of being correct. So why are these different? It goes back to the idea of this. When I'm in a high hazard rate, there's only a really little bit of evidence that's relevant. So I need to forget about everything that I saw before this, which means that I'm going to need to update really fast. But because I only have a really small amount of evidence, chances are I'm not going to do great. I can't have as much confidence, so my accuracy is never going to be as high. In contrast, if I'm in this really low hazard rate environment, I have a lot of information to make me really confident. But in order for me to believe that I am actually in a different state, it's going to take me a while to give up on a lot of this past evidence. So that's where these ideas come from, of having these two metrics, and averaging, of course, across this behavior gives us something meaningful. So now, if we want to assume that we're updating, right? We are learning about that hazard rate. We can use this metric and actually take it one step further. So now, what I've done here is I've plotted based off of trial number. So each of these curves represents an early trial if it's lighter green, and a later trial as it's darker green, turning to black. And we see that we actually get a really strong shift. Our recovery slope changes and our steady state changes. This means that our hazard rate belief is changing, right? We're going somewhere in between these two. So what this allows us to do is quantify how important understanding that hazard rate is. And so what we can do now is just lay out a matrix. So let's just walk through what it is we're seeing. So we have evidence strength. So we can look at either hard to detect change points and easy to detect change points, and how similar is our high and our low hazard rates. So less similar or more similar. And we can just look at how different is this light green to this black, right? How big of a learning curve is there? And what we see is that when we have these easier change point detections, but not completely easy, and when they are more different, we get these greater gains in learning hazard rate. So this allows us to do a few different things. By being able to use this average approach, we built features that interpreted the behavior of the model. And this told us something about when is hazard rate learning important, how do we do it, and if we want to test this in humans now, what are the kinds of questions that we need to ask? Where should we be looking? And what sort of results would we expect? So now, this is a project that's ongoing, and now we're actually working towards the idea of giving this to human subjects and seeing how well can they actually learn these different hazard rates. All right, any questions on the evoked behavior uses? Okay, so then the last thing that I wanted to present to you is sort of these new directions. How do we combine what it is that we're talking about? So thinking about these evoked potentials, where we think about a task, and we're going to use the features of that task or behavior and compare that to the neural data. So we're going to now take a step forward towards really combining these two in a meaningful way. All right, so what do we got to do first? Well, let's talk about what the task is and the kind of question that we want to ask. So we're going to go back to memory, but now we're going to take the question about environment and apply that to memory in terms of context. So what we're going to do is what we can think of as a learning and recall task. And this one is a very special task because not only are we going to do behavior, but in addition, this was done in epilepsy subjects. So we have eye tracking, looking at where a subject's eyes are looking during the task, as well as what size their pupils are. And clinical recordings. So we're going to be looking at actual recordings from the clinically implanted electrodes that are used for detecting where their seizures are starting. But in this case, we can also use it to look at what's happening during these cognitive processes. So what are we doing in this task? Well, there's going to be two halves. There's a learning portion where we're going to get exposed to particular images. So in order to make sure that subjects are actually going to learn and remember some of these images later on, we're going to show them an image. We're going to give them another quick little working memory delay time. And now the question is, did you see an animal? So there's going to be animal images, non-animal images. All they have to say is yes or no. Now in the second half of this, the recognition trial, they're going to see an image, given a delay, and now the question is instead, have you seen this image before? And how confident are you that you've seen it? So what this does is that we can start to develop out and think about what are the strategies we think you'd use? Well, this is memory, so we would assume that you should remember the images you've seen before. But we can also go back to that same idea before of heterogeneity and think of the idea of, well, because I've prompted you for an animal image, you're likely going to weight those more heavily. You're going to remember better an animal than a non-animal you've seen previously. So what does this look like? Well, in this case, this is still pretty preliminary work, so we're still developing out what we want that model to look like. So instead of showing you directly a model that we've built in this case, we're going to talk instead about what does the behavior tell us that will actually support the modeling work. So in this case, we can break it down and look at learning trials and recognition trials separately. And what we're going to look at as a measure is what we call response time. So RT stands for response time, and that's how long after you're prompted did you give a response? In this case, we plotted it as relative response time. So the question is it shorter or longer than your average response time across all trials? And so we can look at a few different computations now. On one hand, in learning trials, we can look at how long did it take you to respond? Is this an animal or not? In early trials, so the first half of your learning block versus your late trials. And so the first thing we notice is, well, your response times are going down, which means that you're learning this task. You're paying attention. Anytime that you're seeing these questions, you're rapidly on it, right? You're engaged. But the other thing that we can see is not only are you engaged, but in general, if there was an animal in that image, you're responding faster. So this tells us that yes, the subjects are performing this task correctly, and they are paying more attention to these animal figures. So now the question we really want to get to is, how does that come out when we're weighting those recognition trials? Well, we can again look at our relative response times. And now in those recognition trials, we have two types of trials. New trials, so new images we've never seen before, and old ones. And we can compare what happens when we were correct or incorrect. And what I just want to point out are two particular features here. So when we're incorrect, but these were new images, so we incorrectly think that we've seen them before, our response time goes way off. There seems to be some deliberation. But the other part that we see is that when we're right and they were old, we're also taking slightly longer. So there does seem to be actual engagement with this task. And to correspond with that, we had asked subjects how confident were they in the responses they were giving. And what we see is that as we have this lower confidence, we're also slowing down, right? So there is sort of this back and forth, there's some sort of engagement. But we wanted to get to the question of, what about those animal images we've seen before? How do those compare? And so if we just look at your accuracy when it's an animal image that you've seen before versus an image you've seen before that wasn't one of those animals, we see that you're doing way, way better in accuracy for those animal images. And if we took that one step further and we say, okay, well, that's great. So this means that you are really having this heterogeneity, right? You're remembering those animal images well. What about when we're wrong? What does that tell us? What we start to see now is that when we're in that incorrect new trial again, right? So this big bump over here, if it was an animal that we're wrong about, we take even longer. So there seems to be much stronger deliberation for that particular subset of images, right? And if we're incorrect for our old images, again, we see these longer delays. So all of this points to the idea that, yeah, all right, we have some sort of heterogeneity. We're weighing our information. We have our animal images that we're caring about. But we care about, what does this mean now in terms of the task and what we can learn about the brain. And so these are very preliminary results, but I just wanted to give you an example of how we can start to think through this. And so this is just looking at our recognition trials again. And we can look at a couple of different locations. So here, I'm just plotting some example. So we can think about this as power of frequency for hippocampus and amygdala. Now, what we're going to do in this case is that we have our LFP, and we're just looking at, essentially, this is a spectral analysis, right? So what are the frequency components of that LFP at and around that triggered event? So we can use two different types of triggered events in this case. When the stimulus comes on, so when we see an image, and when an actual response was given. And so what we're going to look at here, what we see is that there seems to be a lot of activity for stimulus on in hippocampus and at the time of just prior to response, but that there's a difference in amygdala. And so what we see especially that I want to point out is that there is actually this dampening of the activity, right? We don't see as much spectral activity just prior to response in amygdala. But what's more, we have a very fun metric that goes along with this, which is that we had that eye tracking. So there's a couple of ways that we can use eye tracking to align data and understand it. On the one hand, we can look at pupil diameter. So in this case, that's what I've plotted here, is how much does the pupil diameter change in time? And then the other one that we're looking at, and we just started plotting this past week, are gaze data. Where are you looking for how long? And how often do you saccade to those locations? So in this case, what we can see, though, is that there is this relationship just after stim on where the pupil response is very stable, right? So it does seem to be this engagement with the task itself. And then correspondingly, just prior to the response and just after the response, we see these big shifts in pupil that correspond to the shifts in hippocampus and amygdala. So the way that you can kind of interpret this is more about what the underlying frequencies in these bands are. So here we're looking at two bands that are very common in the cognition literature for these. So theta bands, which is low 4 to 8 hertz, and gamma band, which is 30 plus to 90. And we do see that there are these differences between the areas. So this is just going for all of the recognition trials right now, showing that there is this engagement, that there's proof of concept of how we can use this alignment as a way to understand what's going on. But there's a lot of open questions. How can we do this in a more improved way? Well, we can start to look at what are these changes like for the animal and the not animal trials separately. But the other benefit here is rather than just aligning to when a task parameter happens, like the stimulation is on, because we have the gaze data, we can instead align to when are you actually paying attention? When is the gaze data aligned to the image that they're looking at? And then moving forward, how can we start to relate and understand the relationship between these brain regions that are relevant to this task? So this is just giving an example of how we can start to interpret actual neural recordings in the context of a cognitive task. So just to summarize everything and bring it back together, what I hope I showed you today and inspired you with is the idea that we can use these behavioral and these signal processing methods, these complementary approaches, to asking questions about how cognition and neural mechanisms are linked. And by using these more modeling-based approaches, in addition to what we can get from humans, right? So human behavioral responses, it actually allows us this really dynamic back and forth in interpreting those two. So with that, I will leave it open for any other questions, or I'm happy to discuss whichever projects you are interested in.
With respect to the evoked potentials,
Yep.
you have kind of animal and not animal, so that looks a little bit like an oddball paradigm, isn't it? Although the frequency may be equal. Do you also have you compared this to the typical evoked responses at that, the P300? Also, if you present something where you anticipate a reaction, that looks a little bit like the contingent negative variation protocol that people have used, which is kind of related to decision making, isn't it, or alertness, Bereitschaft, as they say in German. So have you kind of compared your evoked potentials with these more classical ones?
Yes, so we started doing some of the classical evoked potential, like the P300, but what we haven't quite gotten to yet, although to your point about the oddball task, I do think it will come in to be of importance, is really utilizing this gaze data. So, right, there's this pupil response for surprise, like images or surprises in the task itself. And so I think that in order to really interpret this data successfully, we actually need to take a step back and first finish interpreting a lot of the gaze responses in relation to the behavior. And then that will help to identify what are the more unique features that we want to explore with the LFP.
Then, of course, another question that comes up is that if you apply this to patients with epilepsy that have implanted electrodes,
Yep.
gives you the advantage of direct cortical activity measurement. The question, of course, is that how relevant is it for people that do not have epilepsy? Have you any ideas on that?
That is an excellent question. So there are a few different things that we are doing that hopefully allow us to answer the question one way or the other. So the first thing I would preface it with is that knowing whether or not someone is doing this in the more typical way is kind of a hard question to answer, because there's a lot of variability, right? You and I can have different but valid cognitive strategies. So it's hard to know whether or not we can really say what's relevant and what isn't for the general population. So how do we go about actually accounting for that? Well, there's a few things we can do. The first one is that these patients, we do have some amount of neuropsych testing on. So we do know whether or not they seem to have decision-making capabilities comparable to what's considered population level. But one of the nice approaches about using behavioral modeling as a complement is that as we can start to extract the actual behavioral strategies that are best matched, so similar to that working memory project where we were using cross-validation, what we can do is say, okay, for this type of a strategy, this is what we are seeing. The other nice thing is that actually there is enough information post hoc about which electrodes are being selected as being the seizure focus that we typically have a number of electrodes that are considered to be outside of the focus. And so we can focus our analyses on the activity in regions that we have no reason to believe would necessarily be severely impacted. We have no guarantees, but by complementing it with this behavioral analyses, it gives us a little more confidence that what's happening is relevant. The flip side of that is looking at someone who is not behaving in the ways that we expect can also tell us something about what is meaningful or important to a particular brain region. Like, what is the role of that brain region in performing a task like this?
Thank you, Tara. I think we have to make a decision about how to decide about all this, but it was a very nice talk, and I am very curious how it will all continue, certainly with the evoked potential component. Thank you.
Me too.
We
All
don't
right.
stop the recording now.